Hey everybody, today's video we're going to cover acidic buffer calculations. So in a previous video you should have watched what a buffer is. So in this one I'm going to show you how we deal with the calculations. The way I'm going to do that is I'm going to compare two other types of reactions we've done. We've looked at weak acids, and this is going to be a conjugate base of a weak acid, and this is actually where we have the buffer. Now I can tell this because one, I have the hydrogen ion here, which tells me that this is an acidic substance. Down here I have the sodium ion, and if you remember, we've talked about this quite a bit. This is referred to as the hydrolysis of salts. So whenever you have an ionic compound, you're looking at the cation and the anion and trying to decide which one of those, anion or cation, came from a weak acid or a weak base. In this case, the sodium ion comes from the sodium hydroxide, which is classified as a strong base, so we ignore that. Sodiums, lithiums, potassiums, calciums, bariums, and strontiums we're going to ignore, and we're going to focus on the anion. Now this anion is connected to this acid up here, which I just said was a weak acid, and I can tell because it's not one of the 7 special ones that I memorized. Also, they give me the Ka right here. Now down here I know this is a buffer because I have that weak acid, right? I've got my weak acid, and I have an ionic compound or a salt that has the conjugate base of that weak acid. So it has that common ion in there. It has that ion that's the same in both of these substances. Okay, so I'm going to do these 3 calculations. I'm going to cut these really short, and I'm going to focus on this one here, and I want to compare the 3 together to see the difference between an acid, a base, and a buffer system. Okay, so to start with here is I have my, what species do I have present? Now this is one way you want to analyze what you're looking at. You're always going to have something in water, and keep water in there because it's going to have an effect every so often. In this case we have the weak acid, you could say, is reacting with that water. If I had a strong acid here, then I would be writing those out in ion form. Okay, but since I don't have the strong acid, I have the weak acid, I'm going to keep it the way it is. So I'm going to write the reaction that goes with this. Okay, so I wrote the reaction that's occurring in the solution. I chose to write it with water this time to create the hydronium ion. Typically I don't do that. I drop out the water on both sides. What I just have is the dissociation of that weak acid into the hydrogen ion and the anion. So remember that the hydrogen ion is the same as that hydronium ion. Alright, so I'm going to go ahead and I'm going to follow the same pattern that I've done for almost all the weak acid problems we've seen. Okay, so what I did was I plugged everything to the ice table and solved just like we did all your typical weak acid problems. So nothing different here than what we did in the last unit, okay, the last test. Okay, solve for X, and notice, don't forget, in this case, X is that hydronium ion, which is really the hydrogen ion, so I can calculate that X and then plug it into my pH. So what I can see is I just have a typical weak acid problem, pH at 2.94. Alright? So what I'm going to do next is I'm going to go ahead and I'm going to plug in, oh, by the way, don't forget that this drops out because of the small Ka and all that business. So let's go ahead and take a look at part B. Okay, so for part B, what I have here, the major species are going to be the sodium ion, the anion from the weak acid, water, and that's essentially it. So again, this would be kind of like drawing how would I envision this in the solution? I would envision a sodium ion and that C3H5O2 minus anion and water separated from each other. Why? Because this is a soluble salt or an ionic compound that dissolves completely. Remember, lithiums, sodiums, potassiums, all of those dissolve and dissociate 100%. So therefore these are going to be focusing on as ions. And I've said before all year long that this is kind of going to come back up quite a bit. So I know to ignore sodium ions. They don't really do anything because they're those sodium ions that we've been crossing off since the beginning of the year. So they're not going to have anything to do with the reaction. They come from that strong base that tells us that this has no affinity for the hydrogen ion or for hydroxide. Over here, this is a conjugate base of the weak acid. Okay, remember this is the conjugate base of my weak acid. So conjugate base, okay, of this weak acid, of that weak acid that I started with. So that's going to be the reaction. What's going to happen is that C3H5O2 minus is going to react with water. And I'm going to rewrite water as HOH so you can kind of see what's going on. And this is that hydrolysis of salts. So I'm going to have HC3H5O2 plus what's left over, which would be my hydroxide ion. And now at this point, I'm going to just follow the pattern I've been doing through the beginning of ice, of equilibrium. Just plug everything into the ice table. In this case, I'm starting with 0.100 molar, and I think getting to this point is the hardest part for students. Recognizing what's going on in the solution, and all I can tell you is just practice thinking about what's in the solution. Apply what we've been looking at all year. Strong acids, strong bases, soluble salts dissolve and dissociate completely. Anything that is not those particular elements and those ions will stay together as a group. Okay, and it's going to be your biggest clue. 0, 0. So I'm going to go ahead and I'm going to plug everything into this, and then I'll solve it and I'll talk about it. Okay, I've completed the problem, and I'm going to show you some of the important steps or the important points of this. First of all, what I'm doing here is I'm obviously getting rid of X. That's not important. But I'm plugging into the ice table, and I get the same pattern at this point, right? Everything is pretty much the same thing as I did in the part A. But what I'm doing is I'm looking at Kb, so be careful. Don't forget that we're looking at Kb here, not Ka. How do I know? Well, because I have a conjugate base, that's one way. Or the other way I know is that I have OH minus. So both of those things indicate that I should have a Kb in my problem. All right, now here's the other problem. Since I need Kb to solve this, I cannot use the Ka that they give me in the problem. So what I need to do is I need to do a little side step where I actually calculate using Ka what the Kb is by using Kw and Ka. Write that equation Kw is equal to Ka times Kb. Okay, and I solve for Kb, then I can plug that in here, simplify and solve for hydroxide, and then find POH and pH. Now notice, this should be a base, right? So if this is a base, my pH should be higher than 7, and it is. And if you go back and look at what the pH was for the weak acid, it was lower than 7. It was actually something like 2.94, I believe it was. Okay? All right, so that would be a weak acid, weak base. So it's actually kind of a review from the last one. But the last thing I'm going to do is I'm going to show you the real buffer problem here, and you can kind of see the comparison between the three types of reactions. Okay, so just like in the other problems that I'm doing here is I'm listing my major species. What do I have when I put these two together? One of the biggest things students do is they overlook the fact that I have a buffer. I have a weak acid, and its conjugate base is a red flag or an indicator that you have a buffer. So you need to recognize that first. What students tend to do is they try to react these two together in a chemical reaction, and that's not what's going to happen. They're not going to react together. They're going to get to an equilibrium because these are going to have a common ion in here. So as I analyze this, as I analyze my major species, I'm keeping my weak acid together. I don't dissociate into ions. So that's going to be my weak acid. Okay, sodium ions, I just train myself to ignore them. What I have here is the conjugate base of that weak acid, and that's my indicator that I have a buffer, and then water. Now water isn't going to do anything here because the water only really gets in the reaction between, I mean, I'll show you what I'm talking about. Okay, so you could argue that water is in here reacting because it really is, but a lot of times we drop the water out of these reactions. So you're going to see a lot of the book problems and a lot of things chemists do, especially in college, they're going to drop that water out and you're going to have left behind just that hydrogen ion. So you're just going to focus on the dissociation of the acid. You could put water in here and react it, that would be fine, but notice what happens here is I have this and I have this, and if you go back and look at A, you'll see the same thing, that I had the weak acid and its conjugate base in here. The difference is at this time I'm going to start with the 0.100 molar here. This we don't care about. This is 0, but this is going to be 0.100 molar. They're going to both be added to this point. So I'm going to start with the weak acid and the conjugate base, and that's what makes this a buffer. This reacts and takes the base that's added, and this reacts with any added acid. And I'll show you that in the next reaction or the next video, how to handle that. So minus x plus x. I'll go ahead and complete this, and we'll look at it when I'm done. Okay, so I completed everything. I plugged everything into the ice table, and then I just plugged everything into my Ka expression and then simplified where these two dropped out. And what happens here is the x actually becomes equal to my Ka, which is equal to a pH of 4.89. Okay, so don't forget that your hydrogen concentration is equal to x because these two are really the same thing. Okay, all right, so a couple things. First of all, I chose to do this through a Ka, and this is probably the most typical. I'm calling this an acidic buffer because we usually start with our acid. If we have the conjugates, we don't want to start with those. You could write this reaction from the conjugate's point of view, making this a base, going back and using part B as your focal point. But why would you want to do that? Because then you're going to get hydroxide, and you don't want to, we'll have to convert the hydrogen. Since we want pH and we have hydrogen ions here, we're just going to go ahead and use this equation as it is, as a Ka. Okay, so plug this in. Now this is an important point, because look what happens. The concentration of my acid and my conjugate base are equal. When that happens, we have what's called an optimal buffer. An optimal buffer is when you have the equal amounts of acid and conjugate base. What that means is that I can absorb an equal amount of added acid or base. So if I added extra acid or added extra base to this, I can add equal amounts. Okay, you're going to see this is very important when we get to titrations. This is going to be a very important point. So just keep in mind that when these two are equal to each other, when your acid is equal to the concentration of the conjugate, what you're going to have is Ka is always going to be equal to X. Okay, Ka will always be equal to X, and in that case we're going to have something else that'll go on, and then your pH would actually be equal to your pKa. Okay, and again, don't worry about that right now, but just get an idea for the buffers, and this kind of stuff will come up as we move on. Alright, so thanks a lot, guys. I will watch the second video that I'm going to do, which will be on what to do when you add an acid or a base to this buffer system. Okay, thanks a lot.